Hi everyone, and welcome to our channel. It would help us a lot if you liked the video, subscribed to the channel, and shared your thoughts in the comments. Let us know what topics you would like us to cover. Could life exist without quantum mechanics? Today we're diving into one of the most thought-provoking areas of science, quantum biology. Not just how quantum effects might show up in living systems, but a deeper question: is life as we know it even possible without these quantum effects? We're going to cover 6 theories that explore the overlap between quantum physics and biological processes. At the end, we'll evaluate which of these quantum effects might be truly essential for life. Let's begin with the theory of quantum olfaction. Traditionally, smell has been explained through the lock and key model. A molecule's shape determines how it fits into a receptor. But this doesn't fully explain why some molecules with similar shapes smell different. The vibrational theory of smell offers a different idea, that receptors might detect the vibrational frequencies of molecules using quantum tunneling.
Right. The idea here is that when an odorant binds to a receptor, it sets up a system where an electron inside the receptor can undergo inelastic tunneling, jumping from one energy state to another, while losing energy to match the vibrational frequency of the bound molecule. This means the receptor doesn't just recognize the molecule's shape, but also its internal vibrational spectrum. There's experimental evidence supporting this, such as studies showing humans and fruit flies can distinguish between molecules that differ only by isotope, which wouldn't make sense under a purely structural model.
Let's move to magnetoreception, the ability of animals like birds to sense the Earth's magnetic field. The most discussed theory here involves a protein called cryptochrome found in their eyes. It's light-sensitive and may generate quantum entangled particles that respond to Earth's magnetic field. This would mean birds literally see magnetic direction as part of their vision.
Yes. Cryptochrome undergoes a photochemical reaction when hit by blue light, forming a pair of radicals, molecules with unpaired electrons. These electrons become entangled, and their spin states evolve in a way that depends on the orientation of Earth's magnetic field. This changes the chemical reaction's outcome, possibly allowing birds to detect directional information. The key quantum part is the entanglement of the radical pair and its persistence for microseconds in a noisy biological environment. That's far longer than expected, and suggests nature may have evolved to protect entanglement to enable this biological compass.
Next up, photosynthesis. This one is less speculative and more experimentally confirmed. In plants, bacteria, and algae, the energy captured from sunlight is transferred through a network of molecules toward the reaction center where it's converted into chemical energy. But what's surprising is how efficiently this energy transfer happens, sometimes over 95%, and that's where quantum coherence comes in.
Exactly. The absorbed photon creates an exciton, a kind of quantum energy packet. And rather than hopping randomly through the light harvesting complex, this exciton takes advantage of quantum superposition. It effectively explores all possible paths simultaneously in a process called a quantum walk, allowing it to find the most efficient route to the reaction center. Experimental evidence, especially from 2D femtosecond spectroscopy, shows that these quantum coherent states can last hundreds of femtoseconds, even at room temperature, which was unexpected. This coherence is thought to increase the speed and reliability of energy transfer significantly.
Now let's talk about DNA and mutations. DNA replication isn't perfect, and sometimes mutations happen. One interesting idea is that some of these mutations come from quantum effects, specifically proton tunneling within the hydrogen bonds that connect base pairs.
This is based on the idea of tautomeric shifts. In standard DNA, adenine pairs with thymine and cytosine with guanine using hydrogen bonds. Sometimes a proton in one of those bonds can tunnel to a different location, changing the molecular configuration temporarily. If this happens during DNA replication, the polymerase might misread the base and insert the wrong one. These quantum tunneling events are rare, but they introduce true randomness into the genome, potentially influencing evolution. If such events are influenced by temperature or environment, they might even play a role in adaptation.
Now we go deeper into consciousness. The orchestrated objective reduction theory suggests that quantum processes in microtubules inside neurons might contribute to conscious thought and even free will. This idea is more controversial, but it's worth understanding.
The theory, proposed by Roger Penrose and Stuart Hameroff, claims that microtubules, protein structures inside neurons, can hold quantum superpositions. When these superpositions collapse via a proposed quantum gravitational process, objective reduction, they influence whether a neuron fires or not. This could introduce non-deterministic elements into brain activity. The model also suggests that these quantum collapses are not purely random, but based on fundamental quantum geometry of spacetime. It's a bold theory, and while coherence times in neurons are debated, there's growing evidence that quantum states in biological systems can be more stable than previously assumed.
Finally, enzyme catalysis. Enzymes speed up chemical reactions, often by factors of millions. Some of these reactions happen far too quickly to be explained classically, especially at biological temperatures. Quantum tunneling might explain how.
Exactly. In many enzymatic reactions, the particle being transferred, often a proton or an electron, doesn't always go over the energy barrier. It may instead tunnel through it. This tunneling drastically lowers the activation energy needed, letting reactions proceed at biologically useful rates. For example, liver enzymes breaking down toxins or enzymes managing DNA repair rely on this. Without tunneling, these reactions would be orders of magnitude slower, potentially incompatible with life. It's not just helpful, it may be essential.
Let's explore how each of these mechanisms supports life in different, complementary ways. Quantum tunneling and enzyme catalysis is likely foundational. It allows chemical reactions in the body to occur fast enough to support life at all. Without this mechanism, metabolism and essential processes like DNA replication or cellular respiration might not function in real time. Photosynthesis powered by quantum coherence ensures the efficient transformation of sunlight into usable energy. Photosynthesis is arguably the gateway between inanimate and animate, the process that turns photons, pure energy, into the biochemical fuel that drives ecosystems. The fact that this efficiency depends on quantum effects suggests that early photosynthetic organisms may have required quantum coherence to thrive. Proton tunneling in DNA may be one of the subtle ways evolution happens. By introducing a natural randomness in base pairing, it allows mutations that drive genetic variation and adaptation. This quantum source of mutation could be critical not just for evolution, but for a living system's ability to adapt to its environment. Remove quantum randomness and you get a slower, more deterministic evolutionary process, perhaps not fast or flexible enough to adapt to the ever-changing environment, especially in early chaotic Earth conditions.
Magnetoreception through cryptochrome. If organisms couldn't use quantum sensing to read the geomagnetic field, evolutionary pathways requiring long-range navigation or spatial memory might be blocked. That's not the end of life, but possibly the end of highly mobile, spatially aware life, which limits intelligence and ecosystem complexity. Quantum olfaction. Accurate smell detection plays roles in reproduction, feeding, and survival. Without this fine discrimination, predator-prey relationships, mating behaviors, and chemical communication might be drastically less efficient, possibly slowing down the evolution of multicellular coordination. And finally, quantum decision-making in the brain, free will and consciousness. If quantum superposition and collapse in neuronal microtubules play any role, as suggested by orchestrated objective reduction theory, then mind and awareness may literally be quantum phenomena. A purely classical brain may still function, but could it produce self-awareness, intention, or abstract reasoning?
Quantum mechanics might not just influence biology, it may be part of its foundation. It shapes how energy flows, how molecules behave, how mutations form and variation arises, how organisms sense the world, and possibly how decisions are made. Without it, the origin and persistence of life could be much harder or impossible. And if that's true, then the implications stretch far beyond biology. They affect how we search for life elsewhere in the universe, how we understand evolution, and maybe even how we define what it means to be conscious. Thank you for watching our video. We'd love to hear your thoughts and topic suggestions in the comments. Don't forget to subscribe to the channel.